Today's tallest skyscrapers are just over 1,400 feet high. Would it be impossible to build one twice as high? The largest bridges in the world today are around a mile long. Is it impossible to construct one 9 miles long, connecting Europe and Africa? The largest ships in the world today are supertankers and aircraft carriers. But a ship 5 times their size? Impossible. Or is it? In fact, all of these projects are already on the drawing boards. If built, they would be engineering achievements of historic proportions. But they would also present unprecedented challenges. Could they really be built? Would they be safe? And could they withstand the worst that nature could throw at them? Engineering the impossible. Hong Kong, a city of 7 million and growing fast. It's bursting at the seams. By the year 2050, Hong Kong's population will almost double. Where will these people live? Other cities face the same problem. Tokyo, Shanghai, New York, Jakarta, Taipei, Beijing, Bombay. By the middle of the century, all may be unbearably crowded.
The pressure is enormous. I mean, people cannot move in those cities, and the cities are growing and growing massively.
If they keep growing, we'll need 15 new cities a year, each housing 12 million people. That's 15 new Los Angeleses every year for 50 years. But there's simply no room left for that kind of urban sprawl. There's only one place to go. Up. Fast forward 50 years. This is the tallest man-made structure on the planet. Its name, Millennium Tower. It would stand twice as tall as anything built before, a half-mile high. Over 60,000 people would live or work here. Literally a city within a city. Millennium's designers think it represents the best solution for the coming population explosion. But could such a huge structure ever really be built? It would cost $10 billion. It would consume more building materials than any single nation could produce. Construction would take a decade. Who would take on such a seemingly impossible task? One of Millennium's key designers is architect David Nelson.
It would be a massive project, to say the least. And it would be a world project. For to actually realize it, resources would have to come from the whole, all of the globe, Europe, America, Asia, all brought together. The challenge and the motivation for doing it would be to realize one of the world's largest and most complex construction projects.
If built, Millennium would be a staggering 2,755 feet tall, 170 stories. But a project of this scale would encounter enormous obstacles from the beginning. The first problem Millennium's developers face is where to put it. By 2050, there probably won't be a square foot of buildable land left in Hong Kong. But the design team came up with a solution. They decided to put the tower out in the harbor. Millennium's other chief designer is Andy Miller.
If you took it and put it into the harbour or into the ocean, you're not using up any more land, and what you could possibly do is then open up land around the base of the building and start to create parks and do all of those kind of things.
If it could be done, Millennium would add to Hong Kong's limited land base instead of consume it. But there was another problem: earthquakes. What would happen to Millennium if a big one struck Hong Kong? How would such a tremendous structure stand up to a major tremor? It's a crucial question, because building on this scale is unknown territory for architects and engineers. A single unforeseen mistake might mean catastrophic failure. So the design team will draw on centuries of engineering know-how in order to make the building safe. Probably the earliest attempts at high-rise architecture were the Great Pyramids, built 5,000 years ago. At 500 feet tall, this one is impressive for the period. But by today's standards, the pyramids are somewhat impractical. 40,000 workers toiled for decades to place the 2.5 million stone blocks. And when completed, there was room for only one occupant. And he was dead. Things didn't change much for centuries through the 1850s. Through all that time, the essential building materials were stone and brick, and those had major limitations. Stone buildings have to support themselves with their exterior walls. The taller a building, the thicker its walls had to be. So 5 stories was about the limit. Then, suddenly, everything changed. Somebody invented steel. His name was Henry Bessemer. In 1856, he perfected the Bessemer steel converter, which could make 30 tons of high-grade steel in half an hour. Steel was 10 times stronger than stone, and it was lighter. Now engineers could make a super strong, super light skeleton for a building. With steel, the sky was the limit. Well, not quite. There was still one more problem to be solved: stairs. Even if you could build a 30-story building, who would ever climb all those stairs? Happily, in 1853, Elijah Otis invented the hydraulic safety elevator. Otis had a brilliant insight. He knew that industrial titans would covet those top floors as the perfect spots for gazing down like gods on the world they were taking over. His elevator was just the chariot to take them to those rarefied heights. The race for the sky was on. The first steel skeleton skyscraper was Chicago's home insurance building in 1885. New York's Flatiron Building was completed in 1902. At 22 stories, it was never the tallest, but its triangle shape still attracts sightseers. By the late 20s, the streets of Manhattan had sprouted nearly 200 buildings at least as high. The Chrysler Building was finished in 1930. It claimed the title of world's tallest, but only briefly. It was overtaken in 1931 by the Empire State Building. At a staggering 1,250 feet, it became a symbol of 20th century optimism, suggesting that if we put our hearts and minds to it, nothing was impossible. For the rest of the century, city skylines grew to dizzying heights. And a new word was born: skyscraper. Of course, the battle for bragging rights never ends. Today's tallest building is Malaysia's Petronas Towers in Kuala Lumpur. Finished in 1997, the slender towers are shaped as 8-pointed stars, and they stand 1,483 feet high, if you include the spires. Why the continuing push for greater height? Perhaps it's the simple human drive to rise to the challenge.
There's a natural desire to push forward, building higher, longer, doing things that stretch the imagination. Seems to be something that's been with man for all time.
And yet, as they stretch ever higher, in one way, skyscrapers remain old-fashioned. They're still built by hand. By hands like these, of ironworkers. Millennium's construction would bring in workers from all over the world. They'd be working higher than any have ever worked before. These men are working in Chicago, on one of that city's newest skyscrapers.
Hey, give me that hook over here, then we'll get up on one end.
This kind of work isn't for everyone.
You don't know if you can do it until you try it. And it takes a special breed to be up here.
Iron workers wrestle 5-ton girders into position while dangling thousands of feet up in the air. The only way to get around up here is to walk on those same narrow beams. It's a reality of the business that not everybody makes it to the retirement party.
At all times, you could be killed, or hurt, maimed.
Because it's so dangerous, these workers are supposed to follow strict rules. For instance, the safe way to get around on the beams is to straddle them. But it's an awkward thing to do. So sometimes the workers will just scamper across. It saves time and an aching back. But one slip, and it's an express ride to the ground floor. Iron workers literally stitch the building together, one piece at a time, from the bottom up. To join two beams together, they'll climb up a 12-foot column 100 stories in the air. It's often done without a safety harness because at the top, there's nothing to hook onto. They call this maneuver hanging iron. Most people think that all the hard hats do is follow the plans. But frequently, these workers need to make critical decisions. Their experience and skill can keep a project from falling behind schedule.
We fix the engineer's mistakes. That's why we're called iron workers. We work the iron to make it fit.
As long as there are iron workers like these, who take pride in their work, engineers and architects will continue to build their dreams.
Well, I can look at the skyline and know I took a small part, and I'm proud of that. I really am.
These workers would jump at the chance to work on something as meaty as Millennium Tower.
It's nice.
I think it's
Beautiful
nice.
building, sir.
It's sharp. It's state of the art.
And Millennium will need them, thousands of them. But such a complex project would also require entirely new construction techniques. In fact, building engineers have already begun to automate the construction process. One of the most ingenious systems now in use is called the self-rising factory. Designed by Obayashi of Japan, one of the world's largest engineering firms, this technology might do for skyscrapers what the assembly line did for cars. A weatherproof enclosure is built around a suite of robotic cranes and lifts. The building's structural steel segments are delivered to the site according to a precise schedule. Every piece is labeled with its final position in the building. Guided by a master computer program, a set of cranes lifts each piece to the proper level. Then, the pieces are transferred to a second set of cranes, which moves them to their final location. With the beams held in place, workers can easily bolt them together from the safety of a support platform. When one level is completed, the entire self-rising factory does its self-rising thing, and the process starts again. When the building is finished, the enclosure is lowered onto the top and connected. It becomes the building's roof. For Millennium, the self-rising factory will sit on top of the tower's center core, which will house the elevator shafts and mechanical systems. The outer ring of the building, the living and working areas, will be built the old-fashioned way, by ironworkers performing their high-wire acts half a mile above Hong Kong Harbor. But even with state-of-the-art construction techniques, Millennium Tower will still be an enormously complex project. It will require so much concrete, steel, and glass, it could single-handedly cause disruptions to the global supply.
Because of the scale of it, something like Millennium Tower would use the entire steel production of Japan for a whole year plus. And of course, that's not going to happen. They wouldn't be able to build any cars, they wouldn't be able to build any hi-fis or anything like that at all. So the flow of materials to the site would have to come from global sources. It couldn't literally come from any one region.
And since Millennium would be a truly global endeavor, the completion of the tower would be cause for a global celebration. For the tower's builders, it'll also be the moment of truth. That's because Millennium's radical design might create unforeseen problems that would need to get fixed in a hurry. In fact, a number of recent buildings have reached completion only to reveal dangerous flaws in their design or construction. Boston, 1973. The city's newest skyscraper, the John Hancock Tower, nears completion. But an embarrassing problem with the building has already become apparent. The windows are falling out. One by one, the 400-pound glass panels that make up the building's facade are popping off and crashing onto the streets below. Nobody knows why. The streets are cordoned off as the engineers try to fix the problem. The building becomes known as the Plywood Palace. After years of testing, the problem is finally traced to defects in the window frames. The manufacturer agrees to replace all 10,000 panels at a cost of millions of dollars. New York City, 1977. The brand new Citicorp building opens to great fanfare. But within a year, the building's architect comes to a startling realization. To save money, sections of the building's steel frame were bolted rather than welded as called for in the plans. Because of the building's unusual design, these weaker joints mean that a hurricane-force wind might actually topple the building. The owners bring in an army of welders, and over the next few months, the repairs are made quietly. Disaster is averted. The point is that modern buildings are so complex in their design and construction, even the best architects and engineers can't be sure they've thought of everything. Millennium would be more complex than anything ever built. So its builders won't know for sure the building is safe until it's up. And they'll have little margin for error. Massive tremors have brought down entire cities in this part of the world. Can Millennium's designers make it immune to these upheavals of the earth? It's a complex problem because in all buildings, including Millennium, safety is just one concern among many. Millennium can't be a fortress. It will need to be a home, one that welcomes people in. The plans call for 100,000 occupants and visitors, working or playing inside at any given moment. Getting those people into the building and making sure they have a great experience will be what makes Millennium successful. But how to do it? For the design team, the secret was to bring all the richness of city life within.
If you took a square kilometre of dense 7 or 8 story major city and then brought it vertically, that's Millennium Tower. It's a place to work, it's a place to live, to be entertained, to shop, to go to church, to do everything that you can think of in a normal life.
Nelson and Miller decided to design the tower as a series of vertical railway stations they call sky centers.
Sky centres are focus points within the tower at different levels, where high-speed lifts would go literally straight from ground up to level 30 to 60 to 90, all the way through to the top.
At each sky center, a cluster of cafes and restaurants, theaters and stores would provide entertainment. Health clubs, even schools and medical clinics would also serve the tower's residents. The tricky part will be getting everyone where they need to go fast.
What we're trying to do on this particular building is look for an alternative way of moving people vertically through the building, which is obviously the most important thing. You need to get people up efficiently and quickly.
That's not as easy as it sounds. In a building millennium size, if each elevator stopped at every floor, the elevator shafts would take up 80% of the building. So in Millennium, express elevators will take people from the ground floor to one of the sky centers every 30 floors up. From there, passengers can change to local cars for the floors in between. Companies like Mitsubishi, Otis, and Schindler are already working on the elevators of the future. They've developed high-tech systems with extra thick cables and triple-decker cars that can hold up to 160 passengers. Electromagnetic designs may eliminate cables altogether and even allow elevators to travel horizontally. The key, of course, is speed. And that's a problem, because elevators can already go a lot faster than people can stand. This is NASA's Vomit Comet. It's a specially adapted passenger jet that lets prospective astronauts experience the effects of weightlessness. The plane climbs to over 30,000 feet and then goes into a controlled free fall, simulating the effect of zero gravity for its passengers. An elevator starting at the top of Millennium could plunge fast enough to briefly create this effect. It looks like fun, but folks heading to work with hot cups of coffee in their hands probably aren't looking for this much fun. So elevators are kept to more earthly speeds to keep passengers on their feet. And that's not the only challenge Millennium could present to the physical comfort of its occupants. Because Millennium will do something all skyscrapers do. It will sway. And at nearly 200 stories high, it'll get hit with the most powerful winds on Earth. Skyscrapers need to sway to dissipate the force of those high-altitude winds. But just how much a building sways is a matter of design.
Starting with a tall tower such as this, it's a fairly obvious thing to start with a rectilinear form such as that. One of the big things with tall towers is the performance under wind conditions, particularly high-speed winds at high level. And this rectangular form or square form really is very difficult in terms of the airflow around it. It creates great turbulence.
The problem with a rectangular shape is that it presents too much head-on resistance to high winds. So what's the best solution? Here at Hong Kong University, the School of Science and Technology boasts one of the world's most advanced wind tunnel laboratories.
Now the 3/4 speed.
A leading expert on the effects of wind on architectural structures is Dr. Kenny Kwok.
If you build a rather conventional square cross-section tower of similar height to the Millennium Tower, I would expect it to exhibit very, very large response, particularly in the crosswind directions.
A rectangular building produces wind vortices over its entire height. Those vortices are whirlpools of air that build up on all sides of the building, pushing and pulling it violently.
Oh, you better pull it back, man. 212 again.
Nelson next considered a cylinder, a structure that's uniformly round from top to bottom. Wind flows more easily around a cylinder, but its constant diameter from the ground up still creates problems.
And if the shape is constant from top to bottom, that vortex accumulates together, and that puts massive force into the building, which has to be resisted.
A cone shape eliminates that problem by varying its diameter along the full length of the building.
For the Millennium Tower, it changes shape continuously so that the vortex shedding pattern is not a regular vortex shedding pattern over the entire height of the structures, but it changes according to the diameter of the building, which changes.
Even at wind speeds approaching 200 miles per hour, Millennium's cone shape proves remarkably stable.
Nothing much is happening. Yeah, it's about 10 times less. Actually, more than 10 times less.
And Millennium's shape isn't the only thing that will provide its stability. It will also use a surprisingly simple device that's already stabilizing skyscrapers around the world. It's called a tuned mass damper.
What we have here is, in fact, a simulation looking at the effect of different dampers, how it controls the building vibration. Initially, we have two identical structures. You can see that it will take a little while for the oscillation to die down. If I stop there for a minute and introduce the twin liquid column damper, the shape of the container and the liquid column are designed in such a way that the liquid will oscillate within the column at the same frequency as the structure itself. Therefore, if I give it a deflection, you can see that the one with the damper will stop vibrating a lot sooner than the one without the damper.
Dampers, by creating vibration in the opposite direction of the sway, tend to cancel out the building's movement. And they're not just useful in the wind. They're also crucial in stabilizing the building during an earthquake.
We have two identical buildings here under simulated ground excitation. And you can see that without any additional damping, both buildings undergo vigorous vibration. What I'll introduce here is a sloshing damper on one of the buildings, and I subject the two buildings to the same excitation like before. You can see the building with the twin sloshing damper undergo much smaller vibration compared with the building without the twin sloshing damper.
The shock waves created by an earthquake vibrate the ground at a frequency around 1 cycle per second. Buildings around 10 stories high resonate at that frequency, which is what causes the damage. Because a taller building has a lower resonant frequency, it shakes much less in an earthquake. Millennium's engineers are hoping that the tower is so tall it'll be impervious to a major earthquake. In theory, Millennium will be one of the safest buildings ever built. In theory. But there's only one way that Millennium's designers will know for sure. The year is 2052. Tonight, downtown Hong Kong will be rocked by one of the biggest earthquakes ever recorded. 8.6 on the Richter scale. Millennium is shaken, but it survives. Millennium's designers have proven something. Things that seem impossible today might just become reality tomorrow. The engineering problems have, for the most part, already been solved. Our achievements are limited only by our imaginations. Those who dare to dream big are often called mad. Norman Nixon dreams big. He wants to build a ship 5 times larger than any ship ever built. Its name is Freedom Ship. If Nixon can build it, Freedom Ship would be nearly a mile long, 3 city blocks wide. The cost? A bargain at $11 billion. Freedom Ship is so huge it would need to be built at sea. Thousands of workers would toil for over 3 years to complete it. And when finished, it would weigh nearly 3 million tons. No one has attempted a ship on this scale. Is Norman Nixon's dream impossible? And even if Freedom Ship could be built, there's a deeper question. Why? Why build a floating city? As Nixon tells it, his initial plan had nothing to do with a boat. What he wanted was to create a private community on a Caribbean island.
Originally, we were developing an island in the Turks and Caicos called East Caicos Island. Our plan was to develop it into a free port, but they had a local election and we lost our island. So some people suggested that we search for another island, and some people suggested that we build a floating city. And we weren't too interested in the floating city concept until somebody brought up the idea of moving this floating city from one country to another, so you were setting offshore a different country every week. So it eventually evolved from a floating city into an actual ship. We could sail from place to place. And this creates a new lifestyle. And it's a lifestyle that doesn't exist in today's world.
Nixon became fixated on the idea. Here was a chance to create something completely new. A city at sea.
This lifestyle is one that gives you the opportunity to work and travel at the same time. We have all the amenities that it takes for you to live a good lifestyle on the ship and still travel continuously.
We feel very strongly that we do have a market. No question about it.
At a day-long seminar, Nixon and his team present the project to potential investors. People have come from around the world to hear the pitch.
Freedom Ship is novel and unique, and a true departure from anything that currently exists.
The speaker's message is clear. Freedom Ship will be a fabulous place to live and work. But there's another point they need to make. That Freedom Ship will make money for its investors. If they can't prove that, they won't raise the billions they need to begin construction.
Economics dictate everything. If it's not economically feasible, we're wasting our time.
I'd like for you guys to look this over and give me some comments about what you think about it, what's missing, so forth.
To pay for itself, the team figured the ship had to house over 30,000 residents, some in multi-million-dollar condos. It would need a private school and hospital. The ship had to accommodate 16,000 workers and at least 30,000 visitors a day. It would need hundreds of businesses like restaurants, supermarkets, and retail stores. It would need an airport for corporate jets and docks for private yachts and tourist ferries.
So we took all of these items, we calculated the square footage they would need, and then we backed into the size of the ship. Once we have this community, then we have something that is economically feasible.
We'd like to put a computer center in there too. So
the bottom line, for Freedom Ship to turn a profit, it had to be large. Very large. Just how large would it be? Well, many of history's biggest vessels, the Titanic, the Queen Mary, the USS Nimitz, and the supertanker Yare Viking, would all fit comfortably inside. The ship's size created something of a credibility problem for its designers. The project's structural engineer is Paul Kidwell.
Probably the largest challenge associated with Freedom Ship is to overcome people's impression that this ship is so large that it can't be built.
30 feet here, so you got 30, 60, 90. So you got 120 feet all the way up to here. So you got
It's a valid question.
And what we're going to put in
A scale model is one thing. But Freedom Ship's designers needed to prove to investors that the real ship could be built. The biggest ships in the world are built here in Italy. The Fincantieri company uses state-of-the-art technology to craft the world's most glamorous cruise ships. But the process is incredibly expensive. That's because so much of a ship has to be custom-made. Modern ships are shaped like long, thin wedges to help them slice through the water quickly. And the curved pieces of steel that make up that wedge can't be ordered from a catalog. They have to be made one at a time. Then, they're welded together by multi-million-dollar robotic machines into huge modular sections of the ship. Next, the sections are hoisted, dropped into place, and attached. The final assembly of the ship takes place on a dry dock. Once complete, the dry dock is flooded, and the ship is floated out to sea. Modern shipbuilding methods have been perfected over the centuries, but they won't work for Norman Nixon and his Freedom Ship. They cost too much.
We calculated what we would have to sell the square footage for, and we came up with a number of $1,200 per square foot. And at that level, it just wasn't economically feasible.
Freedom Ship would cost so much to build, hardly anyone could afford to live on it. Nixon needed to find a cheaper way, so he abandoned traditional shipbuilding and turned his attention to other large floating objects. The largest floating object in the world today isn't a ship at all. It's an airport. Japan's experimental Megafloat airport is currently moored in Tokyo Bay. It's over half a mile long and over 200 feet wide. The concept behind Megafloat is surprisingly simple. It's a gigantic barge made up of hundreds of pressurized steel boxes. The boxes are welded together to form an enormous platform, which was pulled by tugboat into position and then anchored securely to the sea floor. Because Megafloat is constructed out of simple, off-the-shelf parts, it was cheap to build. And that caught Norman Nixon's attention.
We changed our philosophy entirely. Instead of following standard ship design philosophy in which you design every piece of steel in a particular manner for a particular location, we decided that we would go with standard off-the-shelf beams and so forth, because steel is actually very cheap.
Nixon wondered, could he build a ship like this from prefab parts? If he could, he'd eliminate the need for custom steel, and his construction costs would drop dramatically.
For us, it works quite well. And instead of $1,200, we got it down to like $400 per square foot. So we realized we had something that was economically feasible.
Using cheaper off-the-shelf parts, Freedom Ship just might work. But there was a trade-off. All that steel would make Freedom Ship very heavy. And it would be so big, no dry dock in the world could hold it during construction. It would have to be assembled in the water. But where? The location of choice turned out to be the Central American nation of Honduras.
There's a tremendous bay called the Bay of Trujillo in Honduras, and it's about 4 miles of protected water. There's very little traffic in the bay, so it turns out this is an excellent location. It's not far from the U.S. where our engineering crew is located.
This will be our first set of railings that we put in here in the center to slide the comm modules in. We'll add additional railings here and additional railings here later on.
So we build the base of the ship in sections about 300 by 400 feet long, and we slide these base sections into the water. We bolt them together until we have the base of the ship.
Freedom's enormous base will be assembled from over 600 steel cells up to 60 feet wide, 120 feet long, and 8 stories tall. The project would consume vast quantities of just about everything.
The ship is going to weigh like 3 million tons. So we use tremendous quantities of steel. We're probably going to be purchasing steel from 4 or 5 different countries. Another one of the largest products we use is drywall. For a period of 2 years, we're going to be one of the world's largest purchasers of drywall. We've got several carpet mills that are going to be producing carpet for us. We're going to be buying this from probably 25 or 30 different countries.
In fact, to ensure an uninterrupted flow of material during construction, Nixon may need to build his own factories. But there's one part of the ship that Nixon won't be able to get off the shelf. Freedom's motors will be state-of-the-art. In fact, they'll more closely resemble jet engines than ship engines. They show just how far the art of seamanship has come since Noah's Ark. For early seafaring civilizations like the Greeks and Romans, ships got around using wind power and manpower, and those sufficed for centuries. Then something happened that changed shipping forever. The steam engine. In 1807, inventor Robert Fulton built the first successful steamboat. 12 years later, the first steam-powered transatlantic crossing took place, and travel by ship was never the same. The 20th century maritime behemoths, like the Queen Mary and the Queen Elizabeth, could cruise all day and night at a brisk 20 knots, powered by efficient steam turbine engines. Nuclear power came on after World War II. It was too expensive for commercial ships, but large Navy ships adopted it, and it's still in use. Today, virtually all commercial ships use huge diesel engines with screw propellers. The technology is reliable, but it has drawbacks. The engines take up a lot of space in the belly of the ship, and the propellers are fixed in place, making the ship awkward to maneuver. But Freedom Ship will change all that. It'll utilize a brand new propulsion system made up of hundreds of small electric motors, each mounted in its own pod. The pods reduce the need for a huge engine room inside the ship. And since they can swivel 360 degrees, the ship can move in any direction it needs to, even laterally. The captain controls everything from a computer screen and a joystick. Each motor will deliver 30,000 horsepower and will cost over $5 million. But even with 100 of them, Freedom Ship will still be one of the slowest ships on the seas because of its 3 million ton weight. Norman Nixon isn't worried about speed.
In our case, speed is not really that important. We circle the world, but it takes us 2 years to make one revolution, so we're not in a hurry to go anyplace. Our particular philosophy would not work with someone who's building a cruise ship. It would not work with someone who's building a cargo ship. But for us, it works quite well.
It works because Freedom Ship doesn't need to go fast. It will slowly circle the globe. Its course keeps it around 12 miles offshore most of the time, so guests can come and go as they wish on one of the many daily ferries. But Freedom will need to cross the oceans, and so she'll have to be able to stand up to the worst conditions imaginable. The year is 2010, and Freedom Ship is in deep trouble. Under the Pacific, a magnitude 8 earthquake has just set off a massive tidal wave, a tsunami racing out in all directions at 600 miles an hour. The killer wave is a monster no ship can outrun, especially the lumbering Freedom Ship. And Freedom is in the worst place imaginable, in relatively shallow water off the Canadian coast, just a few hundred miles from the earthquake's epicenter. Out at sea, a tsunami is nearly invisible to the eye because its gigantic swell is able to spread out over a large area. But when a tsunami approaches land, the shallow seafloor forces the wave up with devastating results. These are the waves that bring massive destruction to coastal communities. One of the worst tsunamis in history hit the Japanese island of Okushiri on July 12, 1993. It began when an earthquake measuring 7.8 on the Richter scale was recorded just off the coast. Japan has endured these massive waves for centuries. In fact, the word tsunami is Japanese for harbor wave. Sometimes, the wall of water can crest over 100 feet. On Okushiri, 400 homes were destroyed. 200 people were killed. Ruptured gas lines caused a massive blaze, which burned for most of the night. In the blink of an eye, nature's fury had reduced this island to rubble. Back on Freedom Ship, a radio alert has just come in, and the captain swings into action.
Seems like that we are in collision course. And,
He knows what he needs to do to save his ship from impending disaster. But he may not have the time. The captain needs to get Freedom Ship out of the shallow water it's in and out to sea, where the tsunami will have less impact. But Freedom's top speed is only 10 knots. And the death wave is racing toward it at 600 miles an hour. Can Freedom withstand the impact? Nobody knows, because the ship was simply too big to test. Many new ship designs are tested here at the U.S. Navy Surface Warfare Center in Bethesda, Maryland. This wave tank, roughly the size of a professional football field, can put ships of every imaginable shape through precisely controlled, perfect storm conditions.
The thing you want to be able to do is test a model of a ship under conditions where you would never put a real ship. Because if you do it with a real ship, you're wrong and everybody's going to die.
These swells may not look like much, but this tank can produce waves up to hurricane force. Sensors on the scale model record data about the ship's roll and sway, as well as twisting and buckling of the hull. From a suspended control booth, operators run hundreds of trials with different sized waves. The data will then be collected and analyzed.
We can look at the operability of a model. That means how well it can perform its mission out in the ocean. We can look at capsize risk. We can look at seasickness. We can look at lateral accelerations, which might mean somebody that gets tossed overboard if the ship rolls too fast.
Tests like these provide crucial feedback to ship designers. The slightest alteration in weight or shape can mean the difference between a vessel that's seaworthy and one that could sink like a rock. Wave action can actually cause a ship to vibrate along its length. A ship must be able to withstand this vibration, or it could buckle and snap.
And where's our heading? Our heading's at 215?
Yep.
Go ahead and take your speed off. Slow her down to 10 knots.
Throttling down.
Okay, let's try Freedom Ship then, Brad.
Today, the facility will try to analyze Freedom Ship by using a computer model. But the ship's dimensions are so large, the computer can't make sense of them.
It's not going to work. Right now, we clearly are estimating way too much sideward movement of the ship, and that's just because it's shallower than what we're used to.
Even a world-class testing facility like this can't really test the Freedom Ship. It's a problem Norman Nixon will need to address.
See, this is going to be a 3-story casino. That is the most valuable piece of property on the ship.
If he can't convince the skeptics, Freedom Ship will remain nothing more than a dream.
Anytime you propose doing something that hasn't been done before, there's going to be people who say you can't do it. If everybody agreed with you, someone would have already done it.
Someone already has. For nearly all of his 86 years, architect Jacques Fresco has been designing cities of the future. Fresco's structures all derive from a simple form that fascinated him as a boy.
When I was about 12 years old, I was looking at a gear on the table, and I saw the cities of the future. I think all inventions are based upon experiences like that. I don't think they come out of nowhere.
Fresco believes that civilization will be forced to colonize the sea if land becomes uninhabitable.
The Earth can only support so many people comfortably, and if the population exceeds the capacity of the land, we're going to have to move seaward and build cities throughout the sea.
Working from his Florida studio, Fresco has spent decades making detailed drawings of his futuristic ocean cities. He also builds prototypes. experimenting continually with new materials. He even lives in one. Fresco's even developed plans for transporting his structures out to sea. They'll be constructed out of modular sections, assembled on land by robots, and then towed to their final ocean destinations. Other structures will be made from high-tech materials called memory metal.
These memory metals can be distorted, twisted, pulled out of shape, and then when a certain temperature is provided, that memory metal goes right back to its original shape.
So buildings made from memory metals can be compressed into small cubes for towing and then snapped back to size upon arrival.
And almost instantaneously, you will see a building erected before your eyes, and no humans working on it at all.
Fresco's vision goes beyond architecture. He sees his cities as tools for fostering humanistic values.
I feel that environment shapes our values. The people we know, the people we identify with. What will drive people in the future? A world without war, without hatred, without bigotry, without prejudice. The future must extend an invitation for all people to join in because the problems affect everybody.
But the problems affecting Freedom Ship right now are more immediate. On the bridge, the captain pushes Freedom's 100 motors to the max. He needs to get to the safety of deep water, where the killer tsunami can't destroy his ship. But he still has less than 100 feet of water under him. And the wave is traveling straight toward him at 600 miles per hour. It seems like Freedom Ship will get her test after all. The captain watches his tracking screens while the crew and passengers prepare for impact. Will Freedom survive? Or is Norman Nixon's dream about to become 3 million tons of scrap metal on the ocean floor? The ship is badly shaken, but she holds. Freedom has passed the test, this time. Floating cities like Freedom Ship may prove irresistible to those who dream big and can pay the price. Other types of floating cities like Fresco's may be a more feasible solution for nations facing exploding populations. Although both may seem fantastic today, visionaries everywhere are engineering the impossible. For hundreds of millions of years, the continents of Europe and Africa have been slowly drifting apart. But in the 1980s, engineers began to dream of rejoining those two continents with a bridge connecting Morocco in northern Africa to Spain in southern Europe across the Straits of Gibraltar. Then a car could drive from Sweden all the way down to the tip of Africa.
Bridges connect people across a river, now across an ocean. put people together instead of separating them. Chinese used to build great walls to separate them. But now they learn to build bridges. They'll connect the people together.
Would it be possible? A bridge across the Gibraltar Straits would have to be at least 3 times taller, 4 times longer, and 6 times heavier than any bridge ever built.
The question of, is the Gibraltar Bridge possible, has been raised time and time again. And it's a perfectly valid question, because nothing like it has ever been built. And the only way you show that it's possible is to build it.
The engineers wanted to put the bridge in the most logical place, where the straits are narrowest. But that would still mean a bridge spanning 9 miles of open sea. Much longer than any other bridge. And there was another problem. The water here is up to half a mile deep. That meant that the piers, the underwater pillars that support the bridge, would need to be twice the height of the world's tallest skyscrapers. And even if they could be built, they might create a massive safety problem. The supertankers that crisscross the straits are hard to steer. And if one of them collided with one of the piers, it could be a major disaster. So a Gibraltar Bridge seemed an impossible dream. Until one brilliant bridge builder took a closer look at the sea floor. He noticed something that all the others had missed: an underwater plateau in the center of the straits. That meant that the bridge's tallest pier, the center one, need only be 1,400 feet high, a buildable length. Suddenly, a bridge across the straits seemed possible. The man who conceived this idea is one of the world's greatest bridge builders. T.Y. Lin came to the U.S. from China in his 20s with a vision.
I think wild things, see, from a human point of view. See. And then I came to America. I had the technological know-how and know how to put things together and make it happen.
Lin's design was ingenious. The bridge would have 3 towers sitting on 3 piers. The distance between the center tower and each outer tower would be just over 3 miles, with another 1.25 miles to each shore. Engineer Mark Ketchum consulted on the bridge design.
One of the most remarkable aspects of T.Y. Lin is that he's willing to think big. Scale has never scared him.
The scale of T.Y. Lin's design for the Gibraltar Bridge dwarfs any other bridge, indeed any other structure, ever built. The towers would soar 3,000 feet, twice as high as the tallest building in the world. It would take up to 10 years and cost up to $15 billion to build the bridge, making it the largest construction project ever. Chuck Syme is the project engineer for the proposed Gibraltar Bridge.
It'll use more concrete, more steel, more cables than any bridge ever built. It is the King Kong of bridges.
If the Gibraltar Bridge were laid over New York City, it would start in downtown Brooklyn, sail over Manhattan, and wind up in New Jersey. Building a bridge is far more difficult than other kinds of construction because it takes place on water. The first part of construction would be especially challenging, building the 3 underwater piers, each as tall and wide as a skyscraper. The piers would begin as hollow concrete shells like these. They would be built on shore, then towed out to sea. The piers would be guided into place with the help of global positioning satellites, then filled with water and slowly sunk to the bottom. This pier for a bridge in Denmark was successfully positioned within 8 inches of its target. But the pier is only 82 feet long. The center pier of the Gibraltar Bridge would be more than 18 times higher. Could it be accurately placed? The answer would come from offshore oil drilling platforms in the North Sea. They sit on top of piers that go down 1,100 feet, almost as far as the center Gibraltar Pier. The piers for oil drilling platforms, like those of bridges, are assembled onshore, then submerged. But maneuvering a concrete pillar the size of a skyscraper in 1,000 feet of fast-moving water is extraordinarily dangerous. In 1979, an oil platform pier imploded as it was being positioned in the North Sea. It caused an underwater earthquake that registered 3.0 on the Richter scale. If a similar accident occurred in the busy Gibraltar Straits, it could be catastrophic. Even if engineers did manage to construct the bridge's piers, they would then face the next enormous challenge: building the 3 towers, the cable system, and the road deck. The Gibraltar Bridge's sheer size and weight meant finding the right cable system was crucial. The designers considered several classic solutions. This was one of them. San Francisco's Golden Gate is a suspension bridge. That means that its road deck is suspended from 2 massive steel cables slung across 2 towers. The cables transferred the weight of the bridge to the towers. The bridge is more than a mile long. It too was considered impossible to build, but it's only a fraction of the proposed Gibraltar Bridge. The main cables of a suspension bridge are a crucial element. The Storebelt Bridge in Denmark is one of the largest suspension bridges in the world. Soaring up to 846 feet, it's the tallest structure in Denmark and spans a full mile. Near each end of the bridge, under the roadway, are massive structures known as anchor blocks. The blocks extend 40 feet below the surface. The blocks are where the cables are locked down and kept taut. Each main cable is actually a collection of 18,600 wires grouped into 37 strands. Each strand is looped around a red steel anchor bolt and forms a continuous loop from this anchorage to the anchorage on the other side of the bridge. Only a quarter of the wires actually support the bridge itself. Another quarter carry the weight of the traffic. The other half of the wires serve as a safety backup. Each wire is less than a quarter-inch thick, but it's made from high-strength steel, so it can carry the weight of a 3.5-ton cargo truck. The cables must be maintained in good condition to stay strong. Engineer Peter Sluska explains how this is done from inside an anchor block.
The most important element that we need to consider in keeping these cables in good condition is to prevent corrosion. And as part of that, this whole chamber is dehumidified in order to keep the humidity level below a level that steel will corrode at.
Work began on the bridge's 2 main cables in July 1996. It was done with a special apparatus called a spinning wheel. It's a kind of tramway that carried strands of wire across the bridge. This kind of work is a perilous high-wire act. A temporary catwalk had to be built between the two towers. Hundreds of feet above the water, workers spun loops of wire into a cable that weighed 9,500 tons when completed. The spinning wheel carried 8 strands of wire at a time, from one anchor block up and over the two towers to the anchor block on the other side. The wires were laid side by side. They couldn't overlap or twist. When the spinning wheel had made more than 2,000 passes, the wires were squeezed together to form a cable, which was wrapped with steel wire, then coated with special paint. It took the workers more than 4 months of 18-hour days, 7 days a week, to spin the bridge's 2 main cables. They used enough wire to encircle the globe almost 3 times. But the cables for the Gibraltar Bridge would require 10 times as much wire. For Gibraltar's designers, that ruled out a pure suspension bridge. The cables would be so long and heavy, it might be hard to keep them taut. They might droop, the bridge might sag, and ultimately collapse. So the designers of the Gibraltar Bridge had to look at another type of support system. It's called cable stay. In a cable-stayed bridge, the cables connect from the towers directly to the road deck itself, rather than to an anchor block as in a suspension bridge. Here in Georgia, a new cable-stayed bridge over the Brunswick River will soon be completed at a cost of $65 million. It's replacing an old bridge which is too low for ships to pass under. Traffic must come to a halt while the middle section is raised to let a ship through. With 20 ships passing under on an average day, that's a lot of waiting. The road deck of the new cable stay bridge will be over 200 feet above the water, so ships and cars can both move without interruption. In a cable stayed bridge, the road deck itself is part of what keeps the bridge up, so it must be constructed with great care. To build the road deck, workers must first lay out a grid of steel reinforcement bars into which they will pour a special mixture of concrete. Construction of this road deck has been ongoing for more than a year. The workers have to pay special attention to the towers. If they build too far in one direction, the imbalance of weight could topple the tower. Today, the bridge's designer and contractor are making an inspection. They'll get off 450 feet above the water. From here, they can get the best overview of the entire worksite.
So, actually, the shadow looks very interesting. Yeah, the current stay cable.
When it's completed, the Brunswick River Bridge will be one of the largest cable stay bridges in the U.S. But it spans only a half mile of open water. The span of the Gibraltar Bridge would be 18 times longer, and its towers would be almost 7 times taller. To the Brunswick River Bridge's chief designer, there's simply no comparison between the two bridges.
I think if you put a Gibraltar right next to this bridge, you can hardly see this one anymore.
But the enormous length of the Gibraltar Bridge would make a purely cable-stayed design unworkable. The 9 miles of road deck over the straits would require so many cables, the support towers would need to be over 1 mile high. That's why the longest cable-stayed bridge ever built, the Tatara Bridge in Japan, spans only about a mile of open water. So the cable-stayed design wouldn't work for the Gibraltar Bridge either. Some engineers suggested that the very idea of a Gibraltar Bridge was a mistake. They proposed an underwater tunnel similar to the 24-mile-long Eurotunnel between England and France. The tunnel idea had a big advantage: maintenance. A bridge requires a whole lot of upkeep. The cables on Denmark's Storebælt Bridge must constantly be checked and repainted. Then there are those pesky light bulbs, all 9,192 of them, which must be changed by hand.
Vi så en gruppe på 3 mand, som jævnligt faktisk.
We're a 3-man crew, and we all love the work, except when it rains or if it's windy. Then we have problems.
Maintaining a Gibraltar Bridge would be enormously expensive, but a tunnel would have its own problems. The tunnel would be able to carry only electric trains. There'd be no way to vent automobile exhaust from a tunnel more than 9 miles long. So the bridge turned out to be the better choice after all. But it would need to have an innovative new design, one that combined the best elements of cable-stayed and suspension bridges. Each tower would then support a half-mile of road deck in a cable-stayed design. The rest of the road deck would be supported by suspension cables. This hybrid design includes another innovation. In the cable-stayed part of the bridge, the cables don't attach directly to the road deck, but to diagonal struts that soar out from the base of the towers. But no bridge has ever been built with diagonal struts this big, and some engineers doubt it can be done.
These diagonal struts have to be very heavy, and that would be a very inefficient and expensive element of that bridge.
And this untested design would span one of the busiest and most dangerous waterways in the world. The spectacular height of the bridge's towers also would raise the risks for the men and women who actually would have to build them. Even working 200 feet above the calm Brunswick River can be very dangerous.
If I concentrate on what I'm doing, then I can get the job done and not really think about falling.
The workers who would build the Gibraltar Bridge's 3,000-foot towers would be especially vulnerable to one of the main threats to any bridge, the wind. Engineer Brian West explains.
On a day like this, we've got light winds, perhaps 10, 15 miles an hour at rough roadway level. But you go up in the air another 3,000 feet, you could be looking at winds in the 75 and 80 mile an hour range. And this will dramatically inhibit your ability to construct.
The Gibraltar Bridge would be pounded by gale force winds from the Atlantic Ocean and dust storms from the Sahara Desert. To survive these winds, the Gibraltar Bridge, like all other bridges, is designed to move.
This is a simulation of the actual movements of the bridge in that very high-speed windstorm, in a 150-mile-an-hour wind. And in order to make the movements of the bridge visible, they've all been exaggerated by about 10 times. The bridge does exhibit some twisting and galloping over the suspended span, but the bridge stays stable in this very big windstorm.
A bridge must move in the wind to survive the wind, but it must not move too much.
It's entirely possible to conceive of a structure that's strong enough to stand up, but moves around too much in the wind under traffic conditions, moves around too much for people to be comfortable using it.
That's what happened to the Millennium Bridge in London. The first new crossing of the Thames in over 100 years opened to much fanfare in June 2000. People immediately noticed the bridge vibrating under them. The bridge actually started to sway as people shifted to keep their balance.
It is actually wobbling. It seems to be swaying.
It was their motion that threatened the state-of-the-art bridge. It magnified the bridge's initial vibrations into dramatic swaying. Much like when everyone in a small boat stands up at once. Within days, the bridge had to be shut down. The Army knows the perils of walking across even the simplest of bridges. When troops cross a bridge, they are ordered to break step and not march in unison. Otherwise, their rhythmic stepping could start a bridge swaying. When it comes to the dangers of high winds, every bridge designer has one famous catastrophe in mind. Puget Sound, Washington State, July 1st, 1940. Opening day of the $6 million Tacoma Narrows Bridge. From the start, the bridge rollicked in the wind. Tourists would come to ride the wave of the bridge they called Galloping Gertie. 4 months later, when the wind speed reached 42 miles per hour, the bridge had reached its breaking point. Alone on the bridge stood a reporter covering the sensation. He narrowly escaped. But there's another risk besides the wind that would threaten the Gibraltar Bridge: its own weight. The bridge's towers would have to support almost 4 million tons, and then car traffic on top of that. Fortunately, there are emerging technologies which may help engineers lighten the load on the towers. One new technology would build the 14-mile road deck from a surprising material: glass. This is fiberglass yarn, made from thousands of very fine filaments. It's woven into sheets of fabric on giant looms. The fabric is then attached to boards made of lightweight foam. Next, scores of individual strands of the fiberglass yarn are arranged on racks and fed into a special sewing machine. The foam core and fabric are then sent through the sewing machine which stitches hundreds of tiny crisscross structures in the foam core. They will give the panel its internal strength. Now it's ready for the final step. A special resin is injected into the foam core under vacuum pressure.
That resin, in fact, is a glue which is very, very flexible, and it gives it strength much, much stronger than the glass itself.
They test the panel's strength on this machine.
We're at 10,000 load pounds. We're at 15,000 pounds. 20,000 pounds. 25,000 pounds. We're nearing failure. Failure at 27,300 pounds. That's it.
Fiberglass is going to be about 5 times stronger than concrete. Its ability to flex without cracking is much better than a concrete structure. A sudden crash on a concrete deck is going to crack the deck. It's going to collapse. It's very violent. It's very quick and rapid. In a fiberglass bridge deck, there's millions and millions of these fibers, and so they're breaking just one at a time and in bunches at a time. So the sudden impact only creates a local failure. It won't break the whole structure all at once.
The fiberglass panels were given a real-life test on this bridge at an Air Force base in Ohio. The panels were covered with asphalt, so the bridge looked perfectly normal. But it did, in fact, prove much more durable.
Bridge engineers today are embracing fiberglass bridges for their tremendous maintenance benefits. A fiberglass bridge, we believe today, could last 80 to 100 years.
And the time saved during construction would be enormous. Fiberglass panels may become the invention that turns the Gibraltar Bridge from a dream into a reality by promising to dramatically lower its costs. If the bridge did get built and become part of a proposed global highway linking all the continents, would the world become a more peaceful place? Perhaps, but unfortunately, super bridges might also provide new opportunities for super disasters. Every 10 minutes, another ship enters the Straits of Gibraltar. But there are no rules, no traffic cops, no port authority. If a 500,000-ton supertanker were to crash into one of the piers that support the bridge, it could be a major disaster. The center pier would be the most vulnerable because it is the biggest. Its cross-section at the waterline is larger than a football field. The piers of most big bridges are protected by small artificial islands. That way, a wayward ship runs aground before it can hit the pier. But that would not be an option at Gibraltar.
In the situation on the Gibraltar crossing, the water depths, again, are too large and too great to build a protection island to really surround each of the main foundations. Again, we're talking 1,000 feet of water there. So to build an island would really be unprecedented and really impractical.
So bridge designers came up with an innovative protection device, a ring of underwater bumpers. It's a brand new design that's never faced a real-life test. But in the Gibraltar Straits, that test could come very quickly.
You know, you can never really predict when a navigation problem may develop, an engine failure, a loss of steerage, and these can happen, and a ship could possibly run into the tower. And also, in the situation with Gibraltar, you've got water depth surrounding the main towers that is very adequate to carry a ship right into the foundation. So it is a possibility.
The year is 2040. A Spanish family is driving home after a day spent strolling through the bazaars of Tangiers. What they don't know is that the hydraulic system on a giant supertanker 2 miles away has just failed, and it's carrying more than 2 million barrels of crude oil. The captain can no longer steer his ship, which has now become a 1 million-ton torpedo heading straight for the center pier. Back in the car, the family's biggest concern is whether they'll make it home in time for dinner. But if the tanker crashes into the pier, they'll have much bigger worries. Will the bridge collapse? How many thousands of lives could be lost? Down in the engine room, the crew throws the engines into full reverse. But it's gonna take 4 miles to bring a supertanker this size to a full stop. It all comes down to the bumper system. Can it take a hit from a force of 150,000 tons? The bumper system works. And the Gibraltar Bridge, the bridge that was supposed to be impossible to build, stands tall.